Okay, in this example, we've got a cable over here that is inextensible, very, very, very stiff, essentially rigid, and then we have a system over here that is far more flexible, right? Its unstretched length is 0.4 meters. When it's stretched out in the case that we're going to look at, it's 0.45 meters. Right? So it actually extends quite a bit there, and that happens under the loading condition when we apply a 50 kilogram mass. And we're asking from this sort of experimental setup, what is the spring constant that goes with that? And that model is the spring force. If we have a linear elastic spring, Fs, the spring force, is equal to the spring constant times the elongation. Now the elongation again here at delta is going to be equal to 0.45 meters minus the 0.4 meters, or 0.05 meters. That will be important later on. Alright, so let's look at the other pieces of information that we've been provided, right? That we've been given, in addition to the sketch, that our cable AB is 0.5 meters in length, and that in the configuration for analysis, this other side is 0.45, so BC equals 0.45 meters, right? And we also know that the mass, not the weight, but the mass is equal to 50 kilograms. And we're supposed to find K. Right? So free body diagrams are always going to be the useful tool, and of course on the free body diagram are going to be forces, and since we are not given what the value of the applied force is, we have to, let's go find that first. Let's find W, and that's just our simple mechanical model, that W equals mg from physics, of course. We're in the SI system. That makes this a little bit easier to work with. That will do 50 kilograms times the acceleration of gravity, not 9.8, folks. That loses too much resolution. Now if you say 9.806 meters per second squared, that's okay. I tend to use 9.81. That's 3 digits. That gives us enough reasonable accuracy. We'll go ahead and use 9.806 because I've already got it written out, times 50, and that's 490.3 kilogram meter per second squared. And of course that's the definition of a Newton, and so that will be 490.3 newtons after we then of course cancel out the units. Right, so that will give us then the applied force to the system. So now let's go and do, well gosh, I want to do a free body diagram, and I want to do it of this joint. But note, I don't know a single angle anywhere. And so I'm going to say, actually, let's find the interior angles of our triangle that we have up here. And so if, hey, you know, we've got law of sines, and we have law of cosines available to us. Now law of sines will be something like length over the sine of an angle equals the length over the sine of another angle, the angles being the interior angles. But I don't know any angles, and that would require that I know something. But law of cosines, on the other hand, is about the sides of the triangle and only one angle. And I like that, because then I've got all three sides. Why not go and find, say, one of these angles? We'll call that alpha. Right? And so that would be the opposite side. That would be BC squared would equal, the opposite side squared equals one of the sides squared. That would be AB plus the other one, that's AC, minus 2 times the length of AB times the length of AC times the cosine of this angle that we're interested in. And that's going to allow us to go find what alpha is, because we'll put in here, of course, see, BC, that's the opposite one. That's 0.45 squared is going to be equal to AB. That's 0.5 squared plus then 0.7 squared minus 2 times, well, AB was the 0.5. There's your 0.7. There's your cosine alpha. Let's see what we get here. 0.45 squared equals. And then I'm going to subtract off minus 0.5 squared minus 0.7 squared, and that's equal to minus 0.375. That's going to be equal to a minus 2 times 1/2, which would just be 1, and 0.7 times cosine alpha. So that means, of course, that the minus signs, I'm going to divide through by -1, will go away for us nicely. That's good, because I kind of want to have a positive angle here. And then we take the inverse cosine, and in degrees we find out that alpha equals 39.84 degrees. I'm going to keep a few digits there for accuracy reasons. Now that just gives us 1. We can then go and get another one here. Let's see. We want to find eventually this little angle, and I think we'll just do this one here. Let's call that we'll call that beta, and we'll call this gamma. So let's redo this. Opposite side would be then 0.5 squared is going to be equal to the adjacent 0.7 squared plus the 0.45 squared minus 2 times 0.7 times 0.45 times cosine of, this would be gamma. And when we do that, what are we going to get? 0.5 squared minus 0.7 squared minus 0.45 squared equals, divide by 2 divided by 0.7 divided by 0.45 equals, and we got the minus on the minus side again, 0.702 inverse cosine, and we find out that gamma is not 45 but real close. Gamma equals 45.38 degrees. And I'm going to do this one more time, and rather than adding them up to 180 yet, because I'd like to see if I've independently come up with the equations, we're now going to get 0.7 squared equals 0.5 squared plus 0.45 squared minus 2 times 0.5 times 0.45 times cosine beta. See, in class what I would have done is I would have divided up the entire class into 3 groups, and so simultaneously you would have found one of these, and it wouldn't have taken quite as much time as it's taking me as an individual. And we hope beta is going to turn out to be something that works nice. 0.7 squared minus 0.5 squared minus 0.45 squared equals, wow, divided by 2 divided by 0.5 divided by 0.45, there's a minus sign in there, equals that inverse cosine, and we get now the negative sign. You know, keeping track, we ended up with a net positive over here, there's a negative over here, so that we have to be careful. We want the 94.78 value, not the 90 minus that. That would be what, 86 point or 85.21 or 22 or something like that. Alpha plus beta plus gamma would equal 39.84 plus 45.38 plus 94.78, and that would be $180 and change, which is exactly what it's supposed to be. So we got those angles correct. All right. Now I got all of them, and knowing the alpha, well, that shows up here and here, and that will be convenient for the free body diagram of joint B, wherein we're going to go end up finding ultimately B. Let's see, the force in BC is what we want. It's the free body diagram of B that we're going to work with here. So now we go, and we've got our little concurrent force system that's going to form. There's B, and we're going to have the force in AB. Alpha is 39.84, so slightly less than 45 degrees. There's FAB, and then there's, let's see, gamma is just barely more than 45 degrees, turns out. Okay, so there's your FBC, and here's our 490.3 newtons. Right now, we could do components requiring simultaneous equations, or we could do a force triangle. I'm going to choose the force triangle here. That we've got 490 right there, 0.3 of course, and then we go up for FAB and we go over for BC. Now note, it looks like I drew that at 90 degrees. It's not, so don't make that mistake here. And let's see, FAB was at an angle of alpha with a horizontal, so 90 minus alpha would be this little angle right in there, and so that's 90 minus the 39.84, or 50.16 degrees. Right? That's interesting. How about that? FBC is with respect to the horizontal, that's gamma, so this one will be 90 minus that, so 90 minus gamma, 45.38, equals 44.62, and then this one right here would be, of course, the 180 minus the sum of those two. Oh, look at that, the sum of those other two are 94.78, which happened to be the original beta. Really interesting how this is working out. 85.22. There's a complementary thing going on here, very much so. Because just look, the original gamma and beta, or sorry, the original alpha and gamma are right here. They comprise those two, so it really would be the sum of these two that are going to be this angle right in there. Right now I can use law of sines to go find the force. BC. FBC over the sine of its opposite angle is going to be equal to any one of the other ones that we want to work with. Why don't we use 490.3 over the sine of 85.22, and you think I messed up somehow because I didn't include the sine here that I'm just going to automatically throw right over here. This would be sine of the opposite side, 50.16 degrees. So what do we have? 50.16 sine divided by 85.22 sine times 490.3 equals 378. Yeah, let's keep more digits. Equals 377.8 newtons. Alright, intermediate work, so I'm going to keep more. And then finally, that allows us to go find K, because we know from our model that Fs equals K delta, and so therefore we've experimentally measured K as Fs over delta. That's our 377.8 newtons divided by the elongation of 0.05 meters, and we find that we have 7,556 newtons per meter, or we would more properly call that 7.56 kilonewtons per meter, using the significant digits approach that we do in this course. And there's your answer for K.